You must have seen this at least in the internet or some YouTube videos or something. So these are all positive integers, and how their sum can become some rational which is also negative. This just doesn't make sense, right? Does it make sense? Like we want to make, like there are many ways to, like they will give proof for this. There are many ways to prove. Actually, it's not proving that, making a sense out of this. What is the meaning of this? And maybe like there are many other different ways to make sense out of this in physics or in some other geometry. But how number theorists make sense out of this is using the Riemann zeta function. So what is Riemann zeta function? So Riemann zeta function is a series, series given by, like, complex number, real z greater than 1, define this series like this. Then this is analytic function in the real z greater than 1, hence it defines an analytic function, but it is there in the real z greater than 1. So we want to make it in the whole complex plane. How do we do that? So there is one more function, gamma function. This is like it is defined by this integral, and this is like defined in the whole complex plane except poles at 0, -1, -2 and so on. So what this Riemann did was, like, he gave an integral representation for this series that is given by something like this. Like if you consider this gamma of s by 2 into zeta s is equal to, you have s into s minus 1 plus some integral 0 to infinity. Here I have like x power minus half minus s and plus s minus 1. Don't worry about what is this function phi, psi, this is, or like some phi, don't worry about this function, but this integral is exists in the whole complex plane. So initially where we had in the real z greater than 1, there this function will be equal to this integral plus 1 by s into s minus 1, but this is true in the whole complex plane except s equal to 0 and s equal to 1. Now you take this as a definition, so hence this exists in the whole complex plane. So this is, now if you divide these things, if you take it to right hand side, this is your new Riemann zeta function. But the interesting thing here is that if you replace s by 1 minus s, does it change RHS? No. So it is invariant with respect to s going to 1 minus s. So this part what we have here has satisfies the functional equation. If you take this, is same as 1 minus s of that. That is called the functional equation for Riemann zeta function, s going to 1 minus s. But this will give lot of information. What are the informations? So if you go and take it, divide it here, and if you take any negative even integers, this has no pole. Actually, like this is, you take it for granted, this integral has no pole, it's analytic. So this any other things, it has no pole, but are neither 0, neither this of this. So if you approach s to any 2k, negative 2k, this will become, this will be in the denominator and this will have a pole. So zeta will have 0. So zeta minus 2k will be 0. Also, now you have the functional equation where it can have 0. Like this thing will be equal to exactly 1 minus s of this. And we know that like in the real z greater than 1, it has no pole, I mean no pole or no 0, because it is given by a series. Suppose it has some 0 in less than 1. So we have here it is given by a series. So if it has some 0 less than 1, so but this and zeta of 1 minus s are related, right? So by this zeta will have pole in greater than 1. So that cannot happen. So only where it can happen is given by this gamma factors. So only zeros left of 1 are nothing but zeta minus 2k. And where else it can have 0? There can be some areas here where it can have 0. Where it has 0, that we don't know. Riemann himself found out some zeros on real s greater than half, I mean equal to half. This is real s greater than half or real z. I mean, things are in s here, in z in the slides, but they are the same. Riemann found some zeros here, and he conjectured all zeros lie on the real s half line only. There aren't any zeros in between. There is no zero here, there is no zero here. That is famous Riemann hypothesis, which is unsolved, million dollar problem. I think millennium, one of that. So this is the first one. So Hardy later proved that there are infinitely many zeros on this line. But we don't know all. That is still open thing. And there is some region, like say some region of this kind. People know that there isn't any zero here. So other than that, we don't know much. That is Riemann zeta function. Now again, we know the value function like zeta 2k. We know the value. It will be some rational multiple of phi square. Some rational. In fact, I know the value, but I don't remember exactly. But this will be a rational multiple of phi square. But again, zeta 1 minus s is related to delta s. Hence, if you know 2k, you know what? Negative integers, negative odd integers. But what about odd positive integers? That we again don't know. Only thing which we know is zeta 3 is irrational. So since it is a rational multiple of y square, our zeta 2k are transcendental. You know transcendental, right? So they are transcendental. But what about this? We don't even know what is whether it is irrational or not. What we know is, like, I think Aperi proved in 1978 that their zeta 3 is irrational. Later work of Zudilin, like current work as of now, either you take zeta 5, zeta 7, zeta 9, zeta 11. Out of 4, at least there is one is irrational. But we don't know much regarding like which one is irrational. And there are works like if you take all the zeta values and odd zeta values and take a vector space over Q, it's a like infinite dimensional. That in the sense like there are infinitely many irrationals are there, but we don't know like what are those irrational values. That is Riemann zeta. Now if you want to, you know what, like if you want zeta of minus 1, how can you get? If you get say zeta of 1 minus 2. This is that. So if you know that in the RHS, we know in the LHS. So using the values of 2, we know that we can get the values of minus 1. So because we already know its value at minus 2, we know the values of minus 1, and that value is actually minus 1 by 12. Zeta of minus 1 is minus 1 by 12 because of the zeta of 2. Okay, so zeta of minus 1 is minus 1 by 12. Now, is the series valid in minus 1? No. But assume the series valid, just write the series. So at n is equal to minus 1, it will be like how? So 1 power minus 1 plus 2 power, 1 by 1 power minus 1 and so on. That is nothing but 1 plus 2 plus, just write formally, that is 1 plus 2 plus and so on, that is equal to minus 1 by 12. This is the making sense out of it. If you assume that series is true everywhere and you write it as it is formally, then this will give the value minus 1 by 12. So this is, I told, because that's like a fun part of it, and people, you all, if you go to internet and just search 1 plus 2 plus 3 plus is equal to minus 1 by 12, you will get all different kind of proofs, like taking a series and adding to infinite series and so on. Some of them are logically true, some of them are logically illogical, and many things. And many physicists try to, I heard many of the, like one of my friends was saying this is actually true, like this, because it is true, he is giving some physical interpretation of something, I guess. So he is like, he works in, he is a postdoc in the same department, he was saying that is true in few days back. It is maybe true in some different sense for him, like it is true for me with Riemann zeta. So there is one more zeta. What is this zeta? This is Hurwitz zeta. There is one more x, parameter x is involved here. So 1 by n plus x power z. It was in the Riemann zeta, it is just n power z. Here it is n plus x power z. And from here, I have told there is a pole at s minus 1 for this Riemann zeta. This s is going, this pole is going with because of this pole of this gamma function. But at s minus 1 there is a pole, that means at s equal to 1 there is a pole. If there is a pole, we can write Laurent series expansion. So this is the Laurent series expansion of Riemann zeta function, and gamma k are called Stieltjes constants. And similarly we can write Laurent series. The Hurwitz zeta function follows the similar kind of Riemann zeta. So there is a simple pole at z equal to 1. Again we can write Laurent series expansion. But if there is a Laurent series expansion, obviously that x should appear somewhere. That is appearing here in the coefficients. So hence these are functions. They are no more constants, they are functions in x. Now let's stop it there. Let's come to gamma functions which I defined before. You take a logarithmic derivative of this gamma function because you avoid the poles and other places. You call it as psi of x. That is digamma function. That is also very famous function, appears I think in many different branches. Like even the Riemann zeta, not just in number theory, probably like in many other parts of mathematics also it will appear in the physics. This also appear in the in many places. And this will satisfy this functional equation. See, this is a different kind of functional equation. Psi of x plus 1 is equal to psi of x plus 1 by x. And Dilcher generalizes it to bigger scale. We know gamma function given by this integral. This integral. This also has an one limit definition. It's given by a limit of some function. What Dilcher did was, he defined this function. This is limit tending to infinity of this exponential factors. If you put k equal to 0, this matches with our gamma function. This is for all case. This is called generalized gamma functions. Now you do what you have done with the gamma function. Gamma logarithmic derivative of this. That is generalized digamma functions. So it is analogously gamma digamma, generalized gamma, generalized digamma. You have these objects in your hand. And here is the interesting part. Shirasaka proved that these gamma functions, digamma functions, are nothing but this Laurent series coefficient what you had here. These Laurent coefficients and the new functions which we have now are related just by sign. The psi k of x are nothing but minus gamma k of x. Obviously, what is psi naught? Psi naught is psi itself. So this was one of the important result which happened in number theory in last decades. And let it be all. Now you have all these functions. I am going to introduce few more functions. So if you are okay. So what is this? This now we have with one variable we had like zeta functions. There is a multiple variable analogs of this. Like there are many variable analogs of this, but we are interested in three variable analog. This is 1 by n power m1, m power s2, n plus m power s3. There are three variables and double sum. And now it is a three complex variable. In several complex variables, it's not a pole, it's a line. Poles will lie in the singularities are given by lines. So where are the poles of this? Like they just again defined in real s1 greater than 1, real s2 greater than 1, and real s3 greater than 1. In fact, one can show that this is convergent if you just consider real s1 plus s2 greater than 1, s2 plus s3 mutually greater than 1, and sum is greater than 2. That is also enough. But in the whole other complex space, it can analytically continued in whole C3, but the singularities will lie on this line. S1 plus S3 equal to 1 minus L, S2 plus S3 equal to 1 minus L, S1 plus S2 plus S3 equal to 2. These are the lines of singularity for this function. But let's go one step further. Now you tweak in this x for this function. What is the extra thing I have done here? Like we have Hurwitz, along with zeta we had Hurwitz zeta, x has come. With the same thing with n plus m, I have introduced new variable x. Like, right. Here we had Hurwitz zeta. Similarly, I have introduced this. So why I have done that? So let me explain it later. But this will satisfy this kind of functional equation. I mean, if you can see here, S1, like S1 minus 1, S2 minus 1, but there it is reduced, but S3 it is increased. I mean, here it is reduced, but S3 is increased. That you can, just by series manipulation, you can get these two functions. This is a new function which we have considered. But before going there, let's go to earlier function. This is not so well studied. In the sense, for all variables, if you want to know analytic properties of these functions, which you don't know. But when all three variables are same, then this has been studied by Romick, Brinkman and Franke. And in this step, what we consider is, here also we are not studying the function S1, S2, S3. We are fixing first two variable, going with the third variable. This is the one of our main object. You can see, like it is a double series 1 by nm n plus mx for z minus 1. Z is the only variable, single variable. We are back into single variable. So this is the notation theta z comma x we have used. What we have given is that how the singular part. In fact, we have the whole Lorentz series expansion of this function around the pole z equal to 1. Here also this function has pole at z equal to 1, similar to Riemann zeta function. And there we had gamma k, right, as a Lorentz coefficients. Here there is no, it has not been, the function is almost studied, but the Lorentz series expansion is not being studied. Even with the x, when it is not there, even then, when the x is 1, the Lorentz series expansion has not been studied. Here we are giving the Lorentz series expansion with x. And if you put x equal to 1, the classic multiple zeta, that is called Mordell-Tornheim zeta function, because like Mordell-Tornheim had studied in the very long back, they had studied these functions, but after that people have developed. That is called Mordell-Tornheim zeta function. If you put x equal to 1, I think that's not given, but if you put x equal to 1 here, you will get the Lorentz series expansion for Mordell-Tornheim zeta function. So why we are doing this? Like actually that was not our goal to work with Mordell-Tornheim zeta function. Our goal was something different. I will again come to my introduction. So what are two-term functional equations? We have seen something like with Riemann zeta, s going to 1 minus s, that is called functional equation. There is one more functional equation. If you see, what's happening, this is a line 1, what's happening to s going to 1 minus s, it's taking things from here, right, it's matching, it's reflecting on this line. But if I want to reflect like this, like but I mean the infinity should reflect to 0. What is the way to reflect? 1 by x, x going to 1 by x. That will reflect infinity to 0, 0 to infinity, and again the line of reflection will be 1. That is called again two-term functional equation, or that is one of the formula given by Ramanujan, again related to our psi function which we have defined, satisfies this kind of x going to 1 by x. How it is? You consider the psi function, psi of x, and you remove the asymptotic part of that, 1 by 2x minus log x. Now it is summable, in the sense if you take this series, summation, replace x by nx and sum over, because next term will be 1 by x square there in that next term in that expansion 1 by x square. So this series will convergent. So this function f of x is well defined. So now it satisfies this f of x with this term extra term, satisfies f of alpha equal to f of beta. What is f of alpha equal to f of beta? Like alpha beta equal to 1. That is same as saying f of alpha equal to f of 1 by alpha. Correct? So there is interesting thing is it's also equal to this integral. Both f of alpha equal to f of beta equal to this integral. But if you want to prove that, there is something very nice happening here. Assume you somehow you have proved f of alpha equal to this integral. Now f of alpha f of beta will come freely, because if you change alpha to beta here, what happens? This is cos functions. Cos of minus x is cos x. So if you replace alpha by 1 by alpha, so it is minus log again the cos. This will not change. It is invariant with respect to alpha going to beta. So if you prove f of alpha equal to this integral, f of beta is coming very freely. So this is one example of two-term functional equations. There are many other. In fact, modular forms will satisfy this functional equations. But these are two-term because x and 1 by x. There is something called three-term functional equation. They are rare. Like you can get many examples for the two-term functional equations, but not three-term functional equations. But there are some of the very important objects which satisfies this three-term functional equation. For example, again, initially what I have mentioned, like everything is coming back to psi or gamma or zeta. So what I have mentioned, zeta 2m plus 1 or zeta values, we don't know much about that. We don't know the derivation. But Ramanujan gave this very interesting formula which involves odd zeta values. That's why like it's important because it involves odd zeta values. This is this is kind of f of alpha going to f of beta. This is some series. This is again some series, but this is alpha going to beta. Same thing. But this is something extra there. If you consider this as a polynomial, this is in alpha beta, you replace alpha by x, beta by x, you will get a polynomial in x. Correct?
These are Bernoulli.
Yeah. B2Gs are Bernoulli numbers. These are Bernoulli numbers. So that polynomial you can write something like this. That polynomial you have replaced both alpha by beta by like this, and BR are Bernoulli numbers, and this will satisfy both. Two term anyway it satisfies. This also satisfies this functional equation, three term x plus 1. You can see x by x plus 1. And there is mass form, like let us say like a non-homomorphic kind of modular form. If you take that mass form and the Eisenstein series, there is something called period polynomial associated with that. They will also satisfy these three terms. This I am giving some examples which satisfy these three.
What is phi?
This is a period polynomial. Like there are Eisenstein series and mass forms.
It's not that phi, right?
No, not that phi. No. That's a period polynomial that I am not defining. This is nothing to do with that phi. They will also satisfy this kind of three-term equation: x plus 1, x by x plus 1. And Folsom proved that the period polynomial associated with like twisted Eisenstein series, they will also satisfy this three term. These are like, now you have like three examples which satisfies.
What is it twisted?
Even like you have just a character twist. So you will have Eisenstein series, and like with Fourier coefficient we will do just multiplied by character. So here comes the Herglotz and work of Zagier. This will come up with that fourth example for three-term functional equations. So what is Herglotz-Zagier function? If you take psi of nx minus log nx, this is of the order 1 by x, it is not summable. But if you divide by n, now it is order of n square, now it is summable. Zagier proved that these functions satisfies with respect to some canonical limit formula. Canonical limit formula is like finding a constant term of some function, like when you relate a Lorentz series expansion, the constant term finding out that thing is called canonical limit formula. In connection with some canonical limit formula, he proved that this function f satisfies both 2-term and 3-term functional equations. And later, Radchenko and Zagier extensively studied the properties of that function f of x, and they proved that and found the special values of this f of x in some places. And Vlasenko and Zagier considered some different function. This is like, initially it was just n. I mean, here it was n. Now it is n power k, because n power k we need not subtract any terms. So this also satisfies 2 and 3-term functional equation. It looks something like this. This is 2-term, 3-term. Don't worry about the details, but they also satisfy. But what Zagier mentioned that, like, to say that these are rare, he told, like, if ever during your mathematical studies you discover in nature, of course in mathematical nature that is the only thing that's true, anything where there is a x plus 1 and 1 plus 1 by x, that is same as x plus 1 by x, you send me a little email and I will try to fit into the general scheme. And in what follows, we show that the theta function which we have considered before, theta z comma x, satisfies 2 and 3-term functional equation. 2-term is easy, like there is nothing much, but this satisfies also 3-term functional equation. Recall, this is our initial theta function. Yeah, this is how it is. Theta z comma x equal to, this is 2-term. 2-term you can get just by the series manipulation. See, this is x, you just pull out the x and just interchange the role of m and n. This will will come out. This result is like there is nothing to prove in the first one. Second one is quite involved, like I am not proving it, but this looks like this. Again, see, you can see x plus 1 and x by x plus 1. Interesting thing here is, we have this theta z comma 1. If you go to Zagier here, I think I have given in the next slide. Yeah, f of 1. Zagier had this f of 1. We had theta z comma 1. It's the same function at 1. And Zagier had, and Li2 is this function, where z mod z less than 1. He just had Li2, we have the integral involving Li2. That's the analogy with the Zagier's work. And there is a one thing, there is a first part. Next continuation of that is, we consider this function. This is something similar to the Herglotz function. You remember, just a few minutes back I defined Herglotz function. This is a zeta version of Herglotz function, Herglotz zeta version. In the place of psi, now we have zeta. Psi is a Laurent coefficient. Now we have the whole function itself. So this, if you consider this function, this will also satisfy this 2-term functional equation. This is nothing but our theta z comma x. Phi z comma x plus x minus 1 into phi z comma 1 by x is equal to this series. This series is nothing but our theta z comma x. So now if you just add and subtract 1 by z minus 1 and 10 limit z goes to 1 here, this will become minus 5 because these are the Lorentz series coefficients. And this series we can easily say that this is equal to minus f of x. Hence we can get Zagier's result as a corollary of this. But we are interested in something more. What we want, you differentiate and send z to 1. Like if you are just doing that, what you are getting? You are getting the constant term psi. If you are turning z to 1 here. But if you differentiate and then you need to get higher coefficients, right? That's what we are interested. Yeah, sure. Why we are interested? There is a function pi k considered by Ishibashi. This is something similar to what Herglotz function is there. Only thing is that k parameter is extra. If k is 0, it is exactly this function. this function. I mean case 1. And but Ishibashi didn't give any 2-term and 3-term functional equation for that, and it was open for like 20 years to get a functional equation for this. I think here we were able to get 2-term functional equation in an analogy with the f of Zagier. If you consider, you assume like f Zagier f this z phi k in another analogy. Like we have f here, we have phi z comma phi z comma x here, and we have phi k here. So we want to do, actually our initial aim was to get this functional equation for this, but we couldn't able to get it. So what we did, we went with zeta. This involves Hurwitz zeta. We got a functional equation here and differentiate, and turning z to 1, we came back here. So that process we called as Hurwitz lift. I mean, there is no, and it is not actually like it's our terminology. We have used to going here and coming back. Instead of going here, we have called it as Hurwitz lift. That was the word which was there in my title. So this is how the functional equation look like, 2-term functional equation. But if you see, if you want to get it for psi k, you will be having whole finite sum. You can't it like, I think I will go for a special case, then you will easily see. This what is LK here? LKs are given by this integral. There is something more to it, but I will avoid now. Case k equal to 0 is Zagier. Let's see k equal to 1, how it looks. We want it for psi 2, k equal to 1, pi 2, but we won't get it for just for pi 2. We get for 4 like pi 2 as well as pi 1. If you want to get it for pi 3, you will have pi 3, pi 2 and pi 1. It's like it starts from pi 1 to wherever you want, but not exactly one of them which you want. I mean, at least we couldn't able to get it. This is 2-term, and there is one more similar thing. 3-term, we got 2-term. We also wanted 3-term because Zagier had 3-term, and we had 3-term for this. Our theta z comma x, we had 3-term. We wanted to get a 3-term for this as well, but unfortunately we are not able to get it. But what we could able to get it is a 3-term for derivative of that function with respect to x. Their derivative of with respect to z initially we have taken. Here derivative with respect to x. With x we could able to get a 3-term. But why it is interesting if it is just a derivative, not the actual function? Guinan studied exactly the same thing. That was like when we saw it, so we were like surprised. Like Guinan gave a 2-term functional equation for psi, and this is nothing but if you put j equal to 0, I mean j equal to 1, this will be exactly this. And for psi k, in our one of earlier work we had already given for psi k's higher things, but here we give 3-term. So this is 3-term functional equation for pi k dash for this function, where gamma j are still just constants, and again here involves this finite sum. So this was actually kind of this was not our aim. We got it as a byproduct of our work for this Herglotz function. This is first part of, like, I can say half of my like this work. Another I have is little bit different from that. How much time I have? 20 minutes, no? 20 minutes, okay. So actually Nomiko studied this integral. This is connected to the Herglotz function which we have seen before. He is given by this, I mean this integral, and it is also connected with, I mean you may not see any interesting seeing this very little bit complicated integrals, but if you see these two integrals, this looks easy, right? So some of the I mean undergrads are like, we should able to, we think that we may able to solve it, maybe like 11, 12. at least for few values, we may able to, if x is say some natural numbers, something we see that we may able to solve this integral, but it's not. So Herglotz, when he considered this his function, along with that he studied this function, this integral j also for 4 plus root 15. It's a quadratic number. For this, he could able to get a value. See how complicated it is. He could able to get it for only this value. He has done it like only for this. Then there is one more integral, that t, which I mentioned. This later considered recently by Muzaffar and Williams. What is special? Again, let me come to that. As I told, by elementary approach you can't solve it. Although it looks very easy, there is no way to get the evaluations. Initially there were only algebraic methods after Herglotz, algebra using algebraic number theory, to get a evaluations for these two functions. But after Radchenko and Zagier, they have found some analytic methods, as well as they have connected that Herglotz integral to Herglotz function by this. But they missed something very interesting thing, which was not difficult either. And we say that like in our work we show that those two are connected, j and t, which I mentioned, those two integrals I will show in a minute. But what Zagier missed, Zagier and Radchenko, was given by Choi and Kumar. If you see j, we don't know how to evaluate even for very few values. But if you take this two-term functional equation, j of x plus j of 1 by x, such a simple thing, log square 2. And if you take t of x plus t of 1 by x, 5 square by 16. And with this, having this equation in hand, this was not so difficult to get it from there. But what we see here, there is a x in LHS. We are not seeing any x in the RHS. Why x is mysteriously missing? That was the one thing we had even the earlier, those Choi and Kumar had doubt why it is missing. Like I asked last time why it was missing before our work was there, and we didn't know why it is missing. Like it is very unclear. In our work, we show that why that is missing. We can see like why it is missing. Also, we show that like this j and t are like not two random integrals; they are connected. So we give a like double infinite family of the integrals, for which these are just two examples. So that's the one thing which I show, and I may have to skip some parts. So for that, what we do, we had this function, Novikov function. We again introduce one parameter z. Now it's a complex function of z as well. So fz x uv is given by this, where v is, if you see the condition, v is not equal to 1. But it is, one can show that this analytic function in real z greater than 0. But if you allow real z greater than 1, just if you consider that place, then v equal to 1 is also valid. And clearly z equal to 1 will be our earlier Novikov function. And the first result with this new function script fz is that there is a series representation for this integral. This is in mod u less than or equal to 1 and real z greater than 1. We will use, like many places we will not able to use real z greater than 0, although it is defined in that case because of the reason which I will tell later. This series representation, as I told, like if mod u less than strictly less than 1, we can take real z greater than 0. And this series representation leads to this following very interesting functional equation for this script fz. Again two term, f of z, again 1 by x of same script fz with x power 1 minus z will be equal to this. Is it similar to something? This is similar to earlier function, there it was only 1. Here u power m, v power m is coming. It is kind of a bigger version of the Mordell-Tornheim which we had in the before. That helps in our unification. What we do, like now you are getting my point, right? We had function t, integral j. Our aim is to connect t and j. Also to show that in their functional equation, t of x plus t of 1 by x, this is 5 square by 16, g of x, g of 1 by x will be equal to log square root. Log square root. Yeah. Why there is x is missing there? This is our aim. So what we do? We consider the integral j r chi1 chi2 z comma x. This has it may be looking scary in the beginning. Again, it's not, because character chi1 chi2, you know characters, right? These are like homomorphism from z by n, like z by n z star to c star. There you have lifted, like it will take values in the root of unity. So like if you take modulus 2, that means your n as 2, character will look like just 1 0 1 0 and so on. So if it is 4, there will be 2 character. Either first one character will be like 1 0 1 0, second one will be 1, and for 2 it's 0. I mean that character of 1 is 1, chi of 2 is 0, chi of 3 is minus 1, chi of 4 is again 0. It will repeat. For each n there will be many characters. After, if you keep on increasing, there will be many characters. And there is something called primitive. Primitive means that character is like, if you see that first one, the character 1 1 1 0 1 0, that was actually repetition of 2. It's coming like there is a character for 4 also, 1 0 1 0 1 0 1 0. It's a character for 4 also, but it's coming from 2. So it's not a primitive character. But this 1 0 minus 1 0 1 0 minus 1 0, it is coming for 4 for the first time. So it's a primitive character. So let chi1 chi2 be deleted characters, and let zeta r to be that rth root of unity, and this is the Gauss sum associated with this character. Then for real z greater than 0 and chi x greater than 0, this integral is defined by this 1 by gamma z as it is. This is the factor which we had always had, log 1 by t, and this one I am telling about, I will tell you about this little later. This is a sum involving Gauss sum, and this is one just a character polynomial, character logarithm. So when chi2 is primitive, when this is primitive, we can separate it out and we can write like this. This sum, this polynomial in t is very interesting thing. Polynomial t occurring in that last equation is called generalized Pecquet polynomial associated with deleted character chi2. This is given by this, I mean this is the symbol which we are using for this. These polynomials are well known and have been studied for over the 2 centuries, done by the Gauss, started by the Gauss, and he used it for like to prove quadratic reciprocity. And the importance of these polynomials lie not only in the arithmetic quadratic number fields, but also in the quadratic L functions. L function, what is this? Like, don't get scared, like I am not bringing one more function, but this is the actually like with chi, initially we had Riemann zeta, chi of n will be extra in the numerator. This is the deleted L function. So it will follow similar properties for like Riemann zeta function. And there is a Riemann hypothesis for this also, which is also not proved, but actually it has been proved in the functional field setting. There will be something called functional fields. There is again Riemann hypothesis there, but there it is proved. That's why people believe Riemann hypothesis is true, but it is not true. Like it is not even proved for this deleted L function either. So Pecquet showed that why this is called Pecquet polynomial, because of this. I'll tell. Before that, like this L function will have an integral representation involving this Fekete polynomial. There is a integral representation involving the Fekete polynomial. This Fekete show that this L function has no zero in the real 0 to infinity, provided this has no real 0 in interval 0, 1. Thus, study of this polynomial may have implications for existence of Siegel zeros. What is Siegel zero? That is a zero very near to, if there is some zero here, this part, in this line, because this shows that like if the Fekete polynomial has no zero, at least we are sure that this line has no zero. We don't know about here, but at least here we are sure that there is no zero. Right? That's what Fekete showed. That's why it may have implications for the Siegel zero. Siegel zero is the zeros which are near to one point. And with that, why you are studying these two new functions? One is script fz, and one is the grand function j r chi1 chi2. J r chi1 chi2 is given by this finite sum of with character sum of the function fz, and then here is the this is analytic because each fz is analytic. This is our main theorem in this section. What it says? Let r be any natural number and greater than 1. Let chi1 chi2 be any digit characters modulo r for real z greater than 1 and x greater than 0. This satisfies again two-term functional equation, but in the numerator here like it is again a kind of Mordell-Tornheim, but here we have Gauss sum, which I defined before. Gauss sum is this. This is the Gauss sum. L chi. Yeah, two-term functional equation will look like this. Further, if chi1 chi2 are primitive, it will be more simpler. It specializes to that j. I will show you like if this character, if you take character suitably, in fact like character modulo 2, if you take, it will become this j, like this j r chi what we have here will become that j if you take chi1 chi2 equal to character modulo 2, 1 0 1 0 1 0, and if you take this chi1 chi2 be character modulo 4, which one? Second character, that means 1 0 minus 1 0 1 0 minus 1 0, that character, the same j will become t.
How do you figure out such a construction?
That was like initially it was not intuitive for us. Initially we also didn't know like why it's coming, but initially we were thinking like this is a character modulo, like we initially figured out this t is coming for character modulo 4. We didn't figure out character, we initially figured out it is sum of 4 the Navico function, sum of 4 Navico function, 1 minus 1 1 minus 1. Then we figured out like it is kind of 4 it's done, 2 it's done. If you take 3, what we get? We thought like let's take 1 minus 1 and 1. We didn't know what is the right combination. Initially we took that, we got something. Okay, let's try for 5. We didn't got anything. We tried for 6, 7, we didn't got anything. We are about to leave, we thought like okay, let's try for 8 and then we will leave. 8 we got something, but that's not matching perfectly. Then we understood that like we are taking just 1 minus 1 1 minus 1 1 minus 1 for 8, and we thought it may not be right combination 1 minus 1. We may have to take some different combination. Then we are even forgotten z. Without z we were trying to do. Then we introduced z also. Then also we didn't got anything. But then we somehow one day figured out it could be character. But character gave nice things. In fact, there was nothing wrong with this. We can do it any periodic function, but things will not be that interesting. You can take any here, like instead of this characters, you can take any periodic function you can still get a two-term functional equation, but that may not be interesting thing. So this is two-term functional equation. How to, like, from here, what was the way to get z goes, j and t was that specialize chi1 and chi2 and specialize z. Z means you take z equal to 1, it will give, at z equal to 1, this will give the j or t. But thing is that RHS is the very delicate object. You can put z equal to 1 here, like I think I have written it here. Before going there, I will say one more thing. So if you take just, if you take x equal to 1 here and chi1 equal to chi2 equal to chi bar, you can add these two integrals, right? Because chi1 equal to chi2 and x equal to 1. These are both are same objects. Twice of these objects will be equal to this. So you will get this. This is similar to the earlier thing which I have shown. The integral representation for the L function, Ls chi. So this is, if you see this, these are analogous. This also has speculative polynomial. This also has speculative polynomial. This is same. Only thing is there is a character for logarithm. Character logarithm. So here the thing which I was telling was that if you want to, which you wanted to, like we wanted to pin z to 1, but that was not a convergent series at z equal to 1. So that was like, that took some work. We had to go in a roundabout way. This I am skipping as there is no time. Like why we couldn't do that, and we had to go in some long direction. We get it into like analytically continue it and go in some other way. But the final part was that, like, okay, yeah, I'll come here. Here if you see, this is what we get after analytic continuation. But if you take r equal to 2 and chi1 chi2 to be character modulo 2 as I told, this will become just a, right hand side will become just these two. This is actually log square 2, because this will be, each term will be log 2, this will be log 2, I mean minus log 2, this will be minus log 2, it will be log square 2, and L left hand side will be j. This is the j function which we had. So this also explains why there is no x. Actually what's happening, like assume like it is true, if you could tend z to 1 just here itself, like I am explaining with the earlier one because there is no time. Like if you tend z to 1, this factor is getting like removed. Here is the only place where there was x. Z is dominating x, so there you won't find any x in the RHS, and you can separate it out each term, this term and this term, and you can get a constant, nice constant. There won't be without any x. This won't be a function. So this is the explanation why there is no x in the functional equation which is given by Choi and Kumar. They had no x in the RHS. So, but and these are connected also through this gr case, and you take special character, you will get j and t. But as I told, beyond j and t, we can do much more. This is again I have written. When it is odd, it will look like this. When it's even, it will look like this. That is not, I mean, it's okay. So why I am doing this? I am just, next I am giving a table. For that sake, I am giving, write this jr chi in different form, that, so that to make it easy for a table. I am giving for different characters how this ar chi phi and the RHS constant looks like. A constant will come when z equal to 1 or z equal if it specifies some value. How it looks like? This looks something like this. So if you see the inside, like j had log 1 plus tx. If you see, if you remember the integral j, where it is? Log 1 plus tx. Next one is tan inverse of tx. The second one, like character modulo 2, we are getting j. character model of 4, we are getting tan inverse of x, and right square it is phi square by 4, but there is 2i here, so that will make it to like, it will multiply 2i inside also, 2i there also, that will become phi square by 4, I mean phi square by 16, 4 into 4.
So how do you explicitly evaluate this?
Right hand side constants. I mean these things, this like actually like we evaluated this in using this theorem lemma which I mentioned here, which I didn't explain much. Using this we explicitly evaluated these things, and RHS evaluation was not difficult because like when this z will become 1, we can separate it with this series, this, and the earlier theorem which I again didn't mention and this didn't explain will give that very explicitly, like I will show you. Where it was? RHS is very explicit when z is 1. So, and so for particular when it is characters, different when it is odd or even, and these values are mostly known for many characters. So I think I am done with the time. There is some concluding remarks, but the interesting fact was like in the second part, connecting these two and explaining the x, and actually like we can get like lot of other identities. For example, like I will show you one. Now you have like this, right? Special, fix some character chi1, some character chi2, some r, and like assume if you could able to explicitly get this, assume for somehow, then you know what is its integral, you have evaluated the integral. Or somehow like if you able to evaluate some particular characters, you could able to evaluate this integrals, then you know the series, because this none of these integrals or the series, although looks easy, they don't have the explicit forms. So for example, one we have what we have shown here. Somehow for some characters, this is I think character modulo 6 if I remember correctly, we could able to evaluate the integral, and when z equal to 1 of course, I mean z equal to 2, other z's we couldn't, then we could able to evaluate the series because of this relation. And similarly, what else we can do? We can differentiate, then put some values. Again, we have got this, because in very few cases we can evaluate some of them. Here we couldn't able to evaluate any of them, but we could able to get these identities. Like that, if you put some different, we can try with different characters, different values of x and z, and can be able to evaluate at least one of them, and we will get the another. Yeah. That's it. Thank you.
Okay, I have one question.
Yeah, sure.
So, when you said that Riemann hypothesis has been proved for the functional field,
Functional field.
the complex number is contained inside your functional field, right? So
Yeah. No. There is hypothesis, and the function itself must be quite different. Like I don't know anything much about the functional field, but like there like everything, even the function definition etc. is like defined in different way.
So what kind of techniques they...
No, I have no idea about function field. I just know that it has been proved there.
Okay.
So there I function field, there's a polynomial, you take that's right, like there's a polynomial field, but how exactly it's defined, how exactly it's proved, and what is exactly the hypothesis, no, I know there is analogous technique, and not technique, analogous things there, but the things, because it is true there, like people mostly hope it must be true here also, but it's not that it's not that as a subcase of that. No, it's not a subcase of that. But I don't know. I don't have any idea how it works there.
So, and the second question is, when you mentioned that, like when you go to the higher, but like, when you take the C cross C, when you introduce a new variable, it essentially gives you a function from not just from C cross. So can you think of those functions, like you have this, it is not defined on the entire complex field, but the complex dimensional vector space is defined if you remove certain singularities, so can you treat this function as some kind of a function from the complex manifolds, and then
you mean this the Mordell-Tornheim function which I defined
all
before?
of those functions? Can I unify this? Can I treat this function not just a C cross C
function, yes. Yes, yeah.
Can I treat this function as some kind of complex dimensional manifold? Complex manifold to C, maybe. Does that kind of make sense?
Yes. Yes, it must be like yes, because like if you those three lines you have to remove,
Exactly.
And like if you consider only C3 minus those line,
Right.
then it will be like
This to some kind of complex.
yes, yeah. But to make it manifold, it will be compact, right?
Compact.
But it may not be. If you just remove these three single line, it won't be compact, I guess, right?
Right. It is not going to be compact.
Compact, but yeah, manifold to this C, you can think of like that. Yes.
So then, okay, so like all of this calculation, like I'm a geometer.
Yeah.
It's very difficult to visualize, right?
Yeah. Right. That another professor in IIT Gandhinagar, Arnab Saha was telling me like when you do this, like another talk I was giving on this modular form regarding this, something related to this, but mainly in modular form, I was giving in the analytic and number theory perspective. He told me the same, like you should see the geometry part of it as well, because he works in arithmetic geometry, and he told like in India, like people don't try to, like number theory people and these geometry people don't try to interact, because there is a lot of geometric aspect to this modular form and this, and I'm not sure how, like what are the geometric aspect here, but if you come to modular form, definitely there are like lot and lot, but there must be some geometry for this also, but I don't know like what are the exact geometry, but definitely you can think of it as like from manifold to C. Yeah.
So is there any other question?
Yeah.
It's not very related to your talk, but the results are impressive. So,
Yeah. Sure. Thanks.
so one question is about the Riemann hypothesis. So is there some general program that people do to try to prove the Riemann hypothesis?
There must be a lot, but I don't know any specifics, like what are the like one thing is like they are like trying to extend this region, what is Riemann, the zero free region which is already there. There is the one is the Riemann zero free region which is known for long. Now there have been like the many extended version of this same Riemann like zero free region. So they have extended. So if one could able to extend it till here, then use the functional equation, we'll get it. It's if you could able assume somehow like you could able to get it everywhere here, it's done. So they are trying only here mostly. So if one way is to extend that zero free region, like push the boundary forward, and second thing is like obviously the proof by contradiction. If the Riemann, like can you get it, like there are assuming the Riemann hypothesis, there are many results, right? And can you get like ulta thing also, like in the sense like if something is not true, then the Riemann hypothesis is not true, and show that that is true. And but other than that, there are somebody like few days back they told like the techniques to prove Riemann hypothesis that is not yet developed. Like he was telling something which I couldn't able to understand. He was saying like if somebody has proved those things, then at least we can say like we are here to prove Riemann hypothesis in few years, like something like that. But yeah, that's it.
So next question is,
Yeah.
did you email Zagier?
Yeah, actually, like what happened was like immediately like, before even submitting our paper, there was a conference in this Germany, and like Professor Dikshit went. So he went with this we have decided to show it to Zagier, and we went and showed this hard copy of him this same result, and because we also wanted to get some idea on like one thing which I wrote in concluding remark also, like we couldn't able to get a 3 term for this, or like mainly 5k. For this we got 3 term, for this we couldn't, for 5 dash we got 2 term, everywhere we got. We wanted to show that like is there any way we can able to get 3 term for that like we asked Zagier, like he told like he told other results are good, but like this, like he told us to send us a copy, but later he hasn't replied back.